Today we start in Chapter 10 with Taylor polynomials. One of the primary uses of Taylor polynomials is to make calculations that are otherwise difficult to do much easier. For example, we might ask how we compute the sine of x. First answer to that question might be to just type it into our calculator or computer, but then we need to answer the question, how does our computer calculate sine x, right? What does the calculator actually do? To see that this is a somewhat difficult question, we need to recall how we define the sine of x. Well, we could use the unit circle, but a typical definition uses right triangles. We let x be the angle that we're interested in finding the sine of. We label the opposite side from the angle x, the adjacent side to the angle x, and the hypotenuse of the right triangle. You may remember from trigonometry the phrase SOHCAHTOA, which tells us how to compute the trig functions, and in particular that the sine is calculated as the opposite side divided by the hypotenuse. So let's think about what this definition actually requires. We have some angle x, and we need to find the opposite side, which means we actually have to measure that side. And then we have to measure the hypotenuse as well. So to figure out the sine of x, we need to draw a right triangle with just the right angle. So that's going to mean we'll get our protractors out. Once we have the triangle drawn, we have to measure the opposite side, divide by the hypotenuse. And in order to get any degree of accuracy at all, we'll have to do an excellent job with those measurements. Well, we know, of course, that our calculators don't draw right triangles and measure sides when we ask it to find the sine of some angle x. So what does the calculator do, right? How does your calculator know what the sine of 3.2 is? Well, one way your calculator can go about computing things like the sine of 3.2 is to use what we call the Taylor polynomial approximation to sine. The idea is that we use a polynomial that is such a good approximation to the sine function that we use the polynomial to do the calculations instead of sine x. If the two are close enough, we won't be able to tell the difference. Well, why polynomials? Well, it's because they're easy to work with. Polynomials only involve multiplication and addition. So if you think about the formula for a general polynomial of degree n, so just as a reminder, the highest exponent in the polynomial is called the degree. So if I wanted to find, say, Pn of 2, well, then that's really just a bunch of multiplying and adding. I would need to calculate 2 to the n, that's just repeated multiplication, 2 times 2 times 2, multiply by the coefficient a sub n, which is here. Do the same thing all the way down to 2 squared times whatever this coefficient is, a2, and then I add up all the results. So if I'm using a polynomial and evaluating a polynomial, unlike the sine function, there's really not that much to it. Something like addition and multiplication, those are things that are relatively easy to program something like a calculator or computer to do. So now since we have discussed why polynomials are easy, or at least relatively easy, for a computer or a calculator to deal with, the real issue is to now find a polynomial that approximates the difficult function well enough that we can replace the function with the polynomial. In other words, if I want to know the sign of 1, what I can do is find a polynomial that's really, really, really close to sine x and calculate the polynomial evaluated at 1 instead. So in general, what we're looking to do is find the world champion polynomial that approximates our function f of x as best we can. That's what the Taylor polynomial is. It's the best possible polynomial approximation to a function for any given degree, and it's going to allow us to make what are otherwise difficult calculations relatively simple. We're going to take a look at a GeoGebra applet that will show us how to visualize Taylor polynomials, sort of what is happening there. There'll be a link to this applet on our Moodle page, so you could play with this as you wish. So the idea here is we've got a function cosine x here, which is typically a difficult function to program a calculator or computer to compute. It has the same drawback as sine x, right? You have to draw a triangle and compute adjacent over hypotenuse to actually get a value. What the app is currently plotting in purple would be the best possible constant approximation to the cosine function near x equals 0. Remember that a constant function we could think of as just a polynomial of degree 0. So there's no x term, no x squared, and so on. There's just a constant term. So that's always going to look like a horizontal straight line. And what we have here is the best possible horizontal straight line approximation to cosine near 0. And we can see that really, really near 0, that's actually not a terrible approximation. All right, next up we're going to find the best possible straight line approximation. In other words, the polynomial of degree 1. Now, it turns out in this case, the best possible straight line approximation is the horizontal straight line we already had from our constant approximation. So that did not change the picture any. Next up, we'll graph the best possible quadratic approximation. In other words, polynomial of degree 2. Well, here we see we're doing much, much better with our approximation. Because I have a quadratic here, the shape of the graph is a parabola. And so we can make it bend downward just like the cosine curve bends downward near 0. Now eventually the parabola has to do a bad job right down here because the parabola has to go off to either minus infinity or plus infinity, and the cosine function doesn't do that. But we can at least see that, say, between x equals minus 1 and 1, there's virtually no difference between the quadratic polynomial in purple and the original function cosine in black. So next I'm just going to show what happens as we add more and more terms in our polynomial. In other words, as we increase the degree to a cubic, a quartic, a quintic, 6th degree, 7th degree, and so on. And we can see that as we increase the degree, our polynomial approximation will do better and better near 0, and it'll do better and better as we move farther out. So here's degree 4. That's a good approximation out to past about minus 1.5 to 1.5. Here's degree 6. Now we're doing a really good job out to about minus 2.5 maybe. And we can see that near 0 we can't even detect a difference now between the polynomial approximation and cosine. That means if we wanted to say do cosine of 1, what we would want is just to plug 1 into the 6th degree Taylor polynomial. That would be easy to compute, and it would be virtually no different than the cosine is. Here's n equals 8, n equals 9, n equals 10, 11, 12. And you can see that now we're off the screen with, say, 24th degree polynomial. We can't see any difference in the screen that we've got pictured here. So now we're going to make explicit the requirements that we need for having a good polynomial approximation. So our general setup is that we have a difficult function we want to approximate with a much simpler kind of function, a polynomial, and we're going to concentrate near x equals 0. So the very first thing we need is for the function and the polynomial to have the same value at 0. Right? Otherwise, we start off already with some error. So our first requirement is the polynomial and the function have to agree at 0. Next up, we're going to require that the graphs of the polynomial and the function have the same slope at 0. Thirdly, we want the graphs for the original function and the polynomial to bend the same way at 0. In other words, to have the same concavity at 0. And we could go a little further. We're going to kind of run out of geometric interpretations, but the rate at which the concavity changes should be the same at 0. So they should both change the way they're bending the same way at x equals 0. So these observations or these requirements sort of lead to our fundamental requirement that all derivatives have to be the same at x equals 0. So if we can arrange for the derivatives of the function and the derivatives of the polynomial to all be the same, that means their graphs start at the same point, have the same slope, bend the same way, the way they bend changes in the same way, and so on, out to whatever derivative we are going for. Our next step is to take our requirements and show how those actually allow us to calculate the polynomial, to write it down. So first off, we're going to determine the very first coefficient, the constant term, for our Taylor polynomial. Start off by reminding us of the general form for the polynomial. And so we are trying to show how we could figure out just the a naught, the a sub 0. Our requirement is that the Taylor polynomial and our function of interest agree at 0. So we plug 0 into our general polynomial, and notice that every term that has an x in it would go to 0. That would leave us with just the a naught term. And so we have our first coefficient determined. Whatever the Taylor polynomial is, the constant term has to be the same as f of 0. Next up, we figure out how to find a sub 1. Right? So that's the linear coefficient up here. So how would we get that term? That's going to come from equating the derivatives at 0. Remember, we require that f prime of 0 and the derivative of the polynomial at 0 are the same. First step is to calculate the derivative of our polynomial. So the derivative of the a naught term, that's a constant, it would just be 0. This a1 comes from the derivative of the a1x term. And then the derivative of a2x squared, we would bring the 2 down and get 2a2x. The derivative of the a3x cubed term would give us this coefficient of 3 in front of a3 and then an x squared. And so all of the terms have this bringing the power down in front, decreasing the power by 1 to get the derivative of each of the terms. Our requirement on the polynomial is that it has to agree, its derivative has to agree at 0 with the original function. Now we're plugging 0 in to our derivative of the polynomial and noticing that all of the terms besides a1 have zeros in them. So Pn prime of 0 is just a1. And because that has to equal f prime of 0, we have our second requirement, that a1, the coefficient in front of x for any Taylor polynomial, has to be the original function's derivative at 0. Now we're going to go through this a couple more times and hopefully find a pattern. So to determine a2, we would have to take the second derivative of our polynomial, plug in 0, and that has to equal f double prime of 0. So here's that work. The second derivative of our polynomial, from the 2a2x term, I just get 2a2. And then from the 3a3x squared, the 2 would come down, I get 3 times 2 times a3 times x, and so on. If I plug in 0, every term past 2a2 has a 0 in it, and I'm left with 2a2 has to equal f double prime of 0. Remember though, the task is to figure out the coefficient. a2 I find by dividing both sides by 2, and so I get that the coefficient in front of x squared for our Taylor polynomial is the second derivative of the original function at 0 divided by 2. Here's a3. Set the third derivatives of the function and the Taylor polynomial equal to each other. And this is how it ends up looking. The third derivative gives me 3 times 2 times a3. And then I would have for the next term 4 times 3 times 2 times a4 times x, and so on. Plugging 0 in wipes out every term except the first one. That is my 3 times 2 times a3 here. That is what has to equal f triple prime of 0. So to solve for the a3, I divide both sides by 3 times 2. And now we're going to start using our factorial notation. Since 3 times 2 is the same as 3 times 2 times 1, which is 3 factorial, and that's really the pattern we're after. We do one more. The fourth derivative of the polynomial we can write down. And then if I plug in 0, everything past the first term would have a 0 in it, and so would vanish. And so requiring that the fourth derivatives are equal at 0, I have a way of determining a sub 4, and it's the fourth derivative of f at 0 divided by 4 factorial. So here's the main result. We can write down any coefficient for our Taylor polynomial by computing the nth derivative of the original function, plugging in 0, and dividing by n factorial. So this provides us with the way of figuring out analytically what the best possible polynomial approximation is to our function. To put this into a sort of general form that we can use as a formula, as long as our function has n derivatives, then the Taylor polynomial of degree n for the function near 0 is, instead of a0, a1, and so on, we use what we just discovered, that a0 is f0, a1 is f prime of 0, and so on. And now the news is that the polynomial we write down in this way is in fact the best possible polynomial approximation to f near 0. So the highlighted formula now is emphasizing that we can approximate f very well by its Taylor polynomial. And notice that there's no limit here on what our n can be. So if I know how to find the derivatives of f, I could just as easily write down the polynomial of degree 100 as the polynomial of degree 10, at least if I'm using a computer. So we'll be able to approximate our difficult function, something like sine x or cosine x, with a much easier function once we get some practice in figuring out these coefficients. In general, the more terms we take, the better the approximation is going to be. As our first example, we're going to take a look at finding the Taylor polynomial for e to the x. So up at the top here, I've repeated the Taylor polynomial formula for reference. And so we see that our job when we're figuring out the Taylor polynomial for e to the x is to figure out these coefficients, f of 0, f prime of 0, then we'll plug in f double prime of 0, f triple prime of 0, and so on. So for example, let's fix things and say we're going to find the Taylor polynomial of degree 4. Once we figure out how to do it for degree 4, then it won't be any harder to get any degree we want, but that'll just give us something, a place to stop. So first up, we need to know f of 0. Well, f of 0 we would get by plugging 0 into the exponential function, and that is 1. Next up, we need f prime of 0. So first we find f prime of x. F prime of x is the derivative of the exponential, but the derivative of the exponential is just itself. So f prime of 0 is also e to the 0, and so that's equal to 1 as well. In the formula now, I need f double prime of 0. So first I need f double prime of x. Once again, the derivative of e to the x is itself. So I get f double prime of 0 equals e to the 0, and that's also 1. And I think we've done enough now to see the pattern. All of the derivatives of e to the x are e to the x. So all of the derivatives of e to the x evaluated at 0 are just 1. Going out to degree 4, our result is e to the x is well approximated by the polynomial 1 plus 1 times x plus 1 over 2 times x squared plus 1 over 3 factorial, which is 6 x cubed, and the last term would be 1 over 4 factorial, which is 24 x to the 4th. And the claim is that this 4th degree polynomial, this quartic, is the best possible 4th degree polynomial approximation to e to the x. So back on our applet for visualizing Taylor polynomials, I've typed in the function e to the x, which looks a little weird up here, but that's the function that's graphed in black. The applet now is going to show us the actual Taylor polynomial for whatever degree we pick, and it starts off with the constant function 1, right? So remember, the functions have to agree at 0. So the best constant approximation to e to the x is just the constant equal to 1. Here's the best straight line approximation for e to the x. So the requirement that their slopes are the same means that the Taylor polynomial of degree 1 is really just the tangent line there, but they have the same value at 0 and they have the same slope at 0. And over here is the Taylor polynomial of degree 1, 1 plus x. Here's the best possible quadratic approximation. So that would be the 1 plus x plus 1 over 2 factorial x squared. Here's the best possible cubic. And then finally, the place where we stopped, the best possible quartic approximation to e to the x. And this is confirming our result, 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. Now we take a look at finding Taylor polynomial for the function sine x, one of the original difficult functions we discussed. And to fix things, let's go out to degree 7 this time. Once again, for reference, the general formula for a Taylor polynomial centered at 0 is at the top of the page. And so we need to set out by figuring out these coefficients. That means we need to figure out all of the derivatives for sine x. First up, f of 0 is the sine of 0. Just plugging 0 into the original function, and that gives me 0. Next, I need f prime of 0. So first I need to know what f prime of x is. Derivative of sine is cosine, and the cosine of 0 is 1. The second derivative would be the derivative of cosine, that's minus the sine. If I plug 0 into minus sine, I get 0 again. Third derivative, my function would be minus the cosine. The third derivative evaluated at 0 would be minus 1. The fourth derivative would be the derivative of minus cosine. That would be minus negative sine. So we're back to sine x. Here's where we have to notice a pattern. I've gone through 4 derivatives for my function and ended up exactly here where we started. That means the pattern is just going to start over. My fifth derivative will be cosine x. So my fifth derivative at 0 will just be 1. The sixth derivative would be minus sine. That gives me a 0. The seventh derivative at 0, that would be minus the cosine evaluated at 0. So that's minus 1. So the pattern is all even derivatives are 0, and all odd derivatives alternate between 1 and minus 1. If I put all that together, then I get that the sine x is roughly 0 plus 1 times x plus 0 over 2 x squared minus 1 over 6x cubed plus 0 over 24 x to the 4th plus 1 over 5 factorial, which is 120 x to the 5th, 0 over 720 x to the 6th, and minus 1 over 7 factorial x to the 7th. In other words, sine x is roughly x minus x cubed over 6 plus x to the 5th over 120, and then rather than calculate it out, I'll just leave the x to the 7th over 7 factorial in my final answer. So out of all the infinite possibilities for a 7th degree polynomial, we have found the best possible 7th degree polynomial that approximates the sine function. Hopefully, even though it'll take some getting used to on on the mechanics of actually writing these down, I hope at some point we can also just appreciate what an awesome result this is. That with a fairly minor amount of work, most of the time, we can find the best polynomial approximation for these functions out to any degree we want. I mean, if you can try to imagine writing down a polynomial of degree 99 and trying to figure out what that ought to be, hopefully we can agree that this is fairly impressive. In our last example, we're just going to show a couple of results for how we can go about using Taylor polynomials to do useful calculations. Let's say, for example, using our previous work, that we needed to calculate the sine of 1, being careful that our calculator would be in radians. Our Taylor polynomial says the sine function is roughly x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. We'll just use the 5th degree Taylor polynomial, so we'll stop here. So the sine of 1 is whatever 1 minus a 6th plus a 1 over 120 turns out to be. Again, that's something that's relatively easy to program into a calculator. And my calculator gives me 0.84166 repeating. Now we can compare that to what the calculator would give us if we just typed in sine of 1. That the sine of 1 is actually 0.841470, and then it continues. But notice that our very quick calculation here, using just 3 terms in the Taylor polynomial, it would have been easy to use more, gives us accuracy for the sine function out to about 0.0002. So about within 2/10,000ths of the actual value, we have calculated the sine of 1. And for the amount of work that this took, that's really an exceptional result. Next, let's use our exponential Taylor polynomial to figure out something like e to the 0.1. So what would that end up being? Well, the Taylor polynomial says we take 1 plus x squared over 2, and let's stop at the 3rd degree, x cubed over 3 factorial, or 6. Using the calculator, I get about 1.1052. Now, if I just evaluate e to the 0.1 on a calculator, then what I get is e to the 0.1 equals 1.10517, and so on. So here, with a fairly minor amount of work, we've calculated something that would generally be fairly difficult to do. All right, if you think about raising e, which is an infinite non-repeating decimal, raised to a decimal, with a fairly quick hand calculation, we can get to within what looks like about 1/10,000th of the actual value supplied here by a calculator. And then remember that if I needed more accuracy, I would just take more terms. I'd go out to 0.1 raised to the 10th over 10 factorial, however long I need to go. It would be easy to calculate using a handheld calculator, and certainly would be easy to program. Well, that brings us to the end of our Taylor polynomial presentation. We'll see next time that if we don't stop at some particular degree, like 10 or 15 or 6, and instead we continue adding terms indefinitely, then we get what's called a Taylor series. A Taylor series will end up being an exact value for the original function instead of just an approximation, and we'll start sorting out how those work next time.